Okay, this is the time we must begin. So
yeah, everybody, I hope you liked your lunch. I saw a lot of people coming to Simon Center. It's a very nice place to be, and you see they are happy to have us. So the first lecture in the afternoon is from Marta Constantinou, and the second lecture on lattice. What is yours?
And for those who freaked out yesterday about coffee, the coffee is included in when you go and get lunch from the Simon Center. Just keep that in mind. Okay, so I came in having one plan for lecture 2, and I had to change things up because we had some discussions. People showed some interest in some modern things about lattice. So I will present some combination and compilation of different things. But 3 things I want to emphasize today is what kind of matrix elements do we calculate on the lattice. The first lecture, I talked about some diagrams that are not Feynman diagrams, but they kind of show the investigations we have. And then using those type of quantities, we can study physical observables. And one thing I will talk about is the proton, and the other one is about X-dependent distribution functions. And I think, I mean, I could say a lot of different things, but I made some choice, but you should do your own research. I mentioned a proton spin crisis. I want to put it out there that we don't know we know it's not a crisis, but it did raises some concerns in the 80s when people were seeing experimental data. So I will guide you through that, even though I was not around the time in terms of research. So there's some anecdotes that are very interesting to hear about. Okay, so how do we study hadron structure? I want to extend where I left last time with the diagrams. From the physics side, also Yoshitaka talked about distribution functions, PDF, GPDs, TMDs. These are different classifications of the partonic content of hadrons. What I want to emphasize is these arrows you see here. There are these different arrows, and of course, the parent quantities, Wigner distributions, which are 5-dimensional objects, is very difficult to calculate. And there are all of these other observables, starting from the simple ones down here, which are 1-dimensional. These are 3-dimensional, and this is 5-dimensional. When I say dimensional, I mean they depend on 5 parameters. And to count that, you have to remember that if you see transverse, it counts for 2. You have X and Y directions in the transverse component. So that is why you see here 3, but in reality, these are 5. For TMDs and GPDs, we have 3 dimensions. And for PDF, form factors, generalized form factors, these are 1-dimensional objects. And basically what this diagram shows, it shows how starting from a quantity that incorporates all of this information, you can start integrating out some of this, and you get more simple, in quotation mark, quantities. And as one would expect, the ones that are 1-dimensional are easier to understand, both calculate on the lattice, but also extract experimentally. Their phenomenology is much simpler than having to deal with 3-dimensional quantities. The other thing I want to emphasize is that when we talk about EIC science, one of the things that comes up very often is the tomography of hadrons, the 3D tomography of hadrons. And with that, we associate basically TMDs and GPDs. I want you to notice that even though there are arrows connecting these quantities, for instance, if you take GPDs, I will come back and show you more about the operators, even though Yoshitaka talked about this in the last couple of days. If I integrate out the X dependence, I can get the momentum transfer squared. If I integrate out everything except the momentum transfer, I get the form factors. If I integrate out anything related to X and T, I get the PDFs, which is only depending on the longitudinal. But one thing that remains here is that TMDs and GPDs, there are no arrows connecting each other. These are two distinct sides of tomography of hadrons. And if you want to get a 3D tomography, you have to study TMDs and GPDs. Both of them are investigated theoretically, experimentally in lattice QCD, and there is a lot of progress that spilled out from the one-dimensional quantities. Now we can talk about two-dimensional, three-dimensional, and so on. So for those who are not familiar with the parameters that appear here, X is the longitudinal momentum fraction, KT is the transverse momentum, and BT is the impact parameter for that. Okay, so we want to study these distribution functions. If you're experimentalists, you talk about cross sections and factorize them to extract this non-perturbative component. You need to talk about DBCS, and I think Yoshitaka talked about this a bit on Tuesday. But if you're a theorist, you need operators and correlation functions that can be related to those physical quantities. And as I said last time, these are defined in Minkowski space. So time has the real notion of time. And according to the Pardon model, we use the infinite momentum frame, and then the PDF, the GPDs, and the TMDs can be extracted from correlators that have non-local light cone operators. And this means that time and distance satisfy this relation. And according to that, we have basically this here is a correlation function that has the external states of the hadron. And then you have inside an operator that probes hadron structure. And for this particular case of PDF, we have the external states to have the same momentum, so there is no momentum transfer. And also the operator here, they have some gamma structure. So this is gamma plus correspond to the vector. So it's unpolarized distributions. And there is W to restore, to have gauge invariance. So it's a Wilson line connecting these fields. And the fields are separated on the light cone. So that's a relation that we use. So we want to do the same for the lattice. For 3 decades, that was assumed impossible because we work on a Euclidean lattice. Remember that if we don't have a Euclidean matrix where we rotate the time, we have an exponential with a complex coefficient, and therefore the integrals do not converge. So the only way to focus on, to be able to use statistical mechanics methods is basically to go around the problem with the real time, introduce Euclidean time, and where t is now I times tau, and therefore you have this relation. And what one notices is that while here you have a range of data, of points that correspond to different values of T and R, when you go into Euclidean space, the only, because of the plus here, the only coordinate that satisfies this relation is basically the trivial one. There is only a unique point. So these light-like lines, they just become one point. And therefore, we cannot study distribution functions on a Euclidean lattice because we cannot access the light cone. So recognizing this for many, many years, people said, okay, we don't know how, we cannot extract this. I can do an operator product expansion on these quantities and extract the Mellin moments of those. That basically gives a series of infinite local operators that contain a covariant derivative. And then you can calculate this on a Euclidean lattice. This is no longer any constraint about being on the light cone, but having all of this now, you can implement this series and reconstruct the original light cone. That was the idea of an OPE. And you have this coefficient here. These are Wilson type coefficients. You define them in MS-bar scheme. They're calculated perturbatively. We know those. So we can, in principle, reconstruct them. We know them from perturbative QCD, not from lattice. And if you look at now at these operators, even though there is OPE, I have talked earlier here about these form factors and generalized form factors, where we basically get rid of the longitudinal momentum fraction and you get only dependence on delta, which is the momentum transfer squared. So these matrix elements now do contain physical information. They are the so-called form factors and generalized form factors. One thing to see here is that you have this series over n, and n is the order of a derivative operator you insert in your matrix element, and you can go from 0, so you have an ultra-local operator, and you have 1 derivative, 2 derivative, 3 derivative, infinite derivatives, and each one with a given derivative, it decomposes according to the symmetry properties of QCD into some measurable quantities. An example of that, if I take the ultra-local limit, so n equals 0, for the proton, this matrix element, if you insert only gamma operators, which is a vector operator, you can have here 2 terms, and these 2 terms are related to the electric and magnetic form factor of the proton. And you have heard yesterday about the proton radius, which is taking the zero momentum transfer limit of the form factors. That's exactly what we can do here. So all of these quantities like charge radii, spin, axial charge, and so on, these are physical quantities that are related to local operators. So when you do OPE, you do not have to extract the full distribution functions. Okay, so considering we cannot get the full distribution functions from lattice QCD, people focus on the Mellin moments, and that has a lot of good advantages. If you look at the various coefficients here, you realize that these are frame independent, meaning that you can impose any kinematic frame and it should give you the same physical quantity. Statistical uncertainties for small values of n can be controlled. They do contain physical information, charge radii, mass, spin, and many, many more quantities. However, there are a lot of limitations, some of which are related to the fact that I did an OPE, meaning I have no longer direct access to all the parameters of the PDF and GPTs because I integrated them out. I don't know anything about skewness. I will come back to what that means is related to the momentum transfer, the direction of the boost, but I will come back to that. But also from the practical side, as you incorporate more and more covariant derivatives, your signal decays because instead of having an operator which is next, the quark fields are very close to each other, you make them very far away from each other. And the gauge noise, remember how the configurations are very, very noisy. So the gauge noise becomes enhanced and I have a decaying signal. Also, looking at these equations, the higher order you have for covariant derivatives, meaning the higher order of the Mellin moment, and as n increases, I have a sum over this n, which means the number of physical quantities, these form factors, increases. So it makes it so complicated to disentangle them. If I have, for the local case, 2 form factors, it means I need 2 independent equations to solve them linearly. If I have 10, I mean, you need 10 independent ones. So that's how it goes. So it complicates a lot of the calculation. Another thing which is very important is that you have these indices here. So if you go to higher melanin moments and you try to renormalize this operator, then you will see that there is power divergence. This means that the coefficients of the renormalization, they carry factors of 1 over the lattice spacing. And we said that we eventually want to take the lattice spacing going to 0, so 1 over 0 approaches infinity. So one has to take care of these divergences before taking the continuum limit, and taking care of these divergences is very, very complicated. We have successfully done that for a couple of cases. So even though it's great, I can get this, this is the electric form factor of the proton. You see all of these data points extracted from the lattice, and these correspond to different momentum transfer. When I say momentum transfer, I mean the momentum difference between the two external states of your matrix elements. You have a bra and a ket, they carry some momentum. That momentum, if it's different, that's what the momentum transfer we refer to, is the difference between the initial and final state. So we can get all of this data very nicely, at least for the lowest moments. This is frame independent, so you can do any kinematic frame you want, and this is very, very successful. However, this is not the distribution function, the full distribution functions. And reconstructing them, because of all the challenges, I cannot calculate high enough melanin moments to be able to approximate this summation that I have all of them. So I have only a few of them. I cannot successfully reconstruct that one. So this is very challenging. Nevertheless, the community was doing the best it can until a decade ago by calculating whatever they kind of have access to, the spin, the mass, the radii, and so on. The last 10 years, there have been some pioneering developments where people thought, wait a minute, maybe there is a way around the fact that I work on a Euclidean lattice. And maybe if I create a correlator that reminds me the one in the light cone, where your quark fields are separated by some distance, and you have a Wilson line here, I can no longer say that this distance is governed by the light cone, but I can certainly calculate on the lattice a matrix element where the quark and anti-quark are separated in the spatial direction. That is not PDF and GPDs and TMDs. This is something else. However, studying those matrix elements has shown that these can be decomposed into some quantities. You see here H, E, I don't know, yes, H, E, H tilde, E tilde, and all of these in pink. And this resembles what you learned from Yoshitaka. Yoshitaka talked about H and E GPDs. You see here H and E quantities. This is not the GPDs yet. But in the similar way that we can do this on the light cone, we can do this for some lattice quantities that maybe we can take advantage of later. So I will come back and explain how this is successful. And that has a lot of challenges in the calculation. The noise is very hard. So what you see here is basically the cost of producing data, different values of the momenta of the external states. This is an important requirement. When you hear about these novel methods, the external states must be boosted. And that's an absolute requirement, because I know that if I have something that is momentum boosted, I can treat that as a Lorentz transformation and make it into the light cone direction. That's the main idea. You have something which is sitting, this matrix element is sitting flat. So if this line here is a z direction, you have an operator which is defined here. But because you have momentum boosted external states, you can do a Lorentz transformation on that and rotate this to be close to the light cone. The larger the momentum you have, the closer you get to the light cone. And that's the idea of these new approaches that are known under quasi and pseudo distributions. Both of them use the same matrix element. So none of them is better at this point in terms of producing matrix elements. There are other methods. I'm not going to go into, I have them summarized here. We wrote with a collaborator the first review. I think, Alexei, you were the editor of this journal. It was a volume that you and Daniel, I think, were writing. So we wrote maybe 100-page review that was pioneering at the time. The field began in 2013 was the first idea. 14, 15 was the first calculation, but nobody believed in that. And it's interesting to see where we were then and where we were a few years later. So a lot of effort goes now into these new methods. You can see more here. The idea, though, is that regardless of the method that you're using, maybe we can develop a platform that incorporates all of this data in the same way as experimentalists, as global analysis incorporate data sets from different experiments. And they know how to take into consideration the different kinematics, the different specifics of the lattice, of the experiments. Okay, let me talk a bit more about why this works. So this is what we calculate on the lattice. The fields are separated in the z direction, so it's spatially separated, not on the light cone. That is not physical quantity. And then you can, two ideas became available, one by Zhang Dongji 2013, quasi-PDFs, that says, wait a minute, this matrix element now is defined in a coordinate space because you can calculate it for several values of z. Z is the length of the Wilson line. It's a separation between quarks and antiquarks, or gluon fields if you're doing a gluon PDF, GPDs, and so on. I will focus on quarks for this talk. But considering that this is defined in the coordinate space, I can do a Fourier transform, get rid of the coordinate space, and I have a momentum-dependent quantity. And that now brings us closer into what happens in physical quantities. We want this to define the X space, and the X space is the Fourier transform of the coordinate space. However, this is not on the light cone. This is not the physical quantity. How can we take that and make it physical? It has been proven very rigorously by many different people that these matrix elements have a lot of good properties. And actually, they have properties that are similar to what you find on the light cone. If you look at the actual PDFs and what we call here quasi-PDFs or pseudo PDFs, all of these, they have the same infrared divergences. And that is great because the infrared regime is not perturbative. However, they have differences in the UV regime. And that also is very positive because the UV regime can be calculated perturbatively. So what these methodologies say is that take now these matrix elements that have the right infrared physics, that have the right non-perturbative physics, and apply a correction to them to make them match them to the light cone. What this means in practice, and I'm not an expert, I am a lattice practitioner, so I take the equations that theories give. But the idea practically is that you do a calculation of in dimensional regularization or another regularization of choice of the light cone matrix elements. You do the same calculation for these now spatially separated matrix elements. You see the divergences, you see their difference of those two, and that is classified as matching. And those who know what perturbative renormalization is, or going from one renormalization scheme to another, that's also can be done perturbatively. So the idea is that you capture perturbatively the differences between these lattice objects and the light cone objects. You apply them on these lattice data, and therefore you match them in coordinate space. That's the main idea. The same matrix elements can be analyzed in different ways. We produce them as matrix elements, non-local operator with a Wilson line, external states boosted, and analyzing quasi-PDFs means you do a Fourier transform on that to go to the X space. Anatoly Radiushkin's idea came a bit later that says, wait a minute, instead of doing that, I can do something else that is equivalent, which is basically introduce the so-called Ioffe time, and that is is the core Z times P. And having that, you introduce what we call Ioffe time, and then you do a Fourier transform from that Ioffe time, which is no longer Z, but is Z dot P. And from that, you can get the X-dependent quantity. So theoretically, from the same matrix element, you can follow one approach or the other approach, you should get the light cone quantity. In practice, there are systematic uncertainties, and we will never going to get the same data, or we're not there yet. So, but this complementarity is really good in terms of testing our systematic uncertainties, testing where each method has strengths and weaknesses. One thing I could mention, for instance, is the renormalization. Every operator needs to be renormalized, and you can, in the case of the quasi-PDS and GPDs, you must calculate the renormalization separately and take care of the divergences by applying renormalization. The pseudo-Ioffe time distribution relies on taking ratios of matrix element. And if you have multiplicative renormalization, A times something over A times something else, A cancels out. So in that sense, you don't have to renormalize. On the other hand, there are other kind of weaknesses. What if you have mixing and it's not A times something, but there is an additive terms? Other things that this has to do it's a large momentum factorization. Remember how I said you need to rotate. You do a Lorentz transformation, and you have to have the momentum high enough. If you don't have the momentum high enough, you don't go very close to the light cone. So the correction here is larger. This is a short distance factorization. So for this to work, Z has to be very small. So practically this introduces some challenges. Nevertheless, both approaches are very useful and valuable. We can get both of them and compare our results. And last thing I want to mention about these approaches is that you might be wondering, but this is matching meaningful? Well, I would say it's not much different, or it resembles what is done with cross-section. When you have a cross-section data, what do? You factorize them. And you have a component which is dependent on the process, and another component here, which is the non-perturbative component. So the fact that you are able to factorize is because of asymptotic freedom, is because you can do perturbative QCD to extract this and separate the two components. Is that something that you're more familiar with? In a similar way, this matrix element and the light cone quantity, they have a lot of, their non-perturbative structure is the same, and their differences are only in the perturbative regime, and therefore we can kind of factorize them. Okay, does this make sense? So it's not a black box, it's not one versus the other, everything complements them. Okay, so going back, this is a summary of what I have shown last time. So how do we calculate these matrix elements I talked about? We calculate this is for the proton, by the way, there are 3 lines, it's 3 quarks. We have a 2-point function, which is basically you allow a proton to propagate in space-time, and you can calculate its energy from that. Or the 3-point functions where while the proton propagates, it interacts with an external probe, in a similar way, you have a lepton-proton scattering, right? You have this probe to get the hadron structure. Theoretically, you need an operator that is going to capture that. So if you want to get the electromagnetic structure, you need a vector type operator. And so all of this you can probe in a naive way. I talked the last time about weak contractions and how these are basically a way for us to remember which terms of the weak contraction we have considered where. But in a first order approximation, sometimes we say, well, you can get the valence vector, you can get the C-quark vector, you can get the gluon contributions, and all of this comes from different diagrams. It's not exactly like this. It's more dirty business, the way you associate them. At the end of the day, if you want to get physical quantity, you incorporate all of them, and that's it. Okay, are there any questions? Was it clear? I mean, the theory, it took 7 years to develop. I mean, even lattice practitioners did not believe others who started working on these things. Now this picture has changed, of course, but I do know that there are a lot of complicated terminologies. I try to say them as simple as possible, but that's not always easy. Okay, so what can we do for from the lattice that can help EIC science? The spin is one example. The mass is a different example. I'm not going to talk about that here, but all of this appeared in the assessment, the NSAC report for the National Academies of Science report for EIC in 2019, and they identified some priority questions such as the mass, the spin, the properties of dense systems, and a hadron structure can address the first two of them. And as I said last time, if you look at the yellow report of EIC that was put after the above report, which is a very long write-up. It incorporates lattice QCD and how we can give input on these quantities. By the way, the things about quasi and pseudo are also mentioned in the report because we want to study tomography. And the only way to do that is to understand GPDs and TMDs. Okay, proton spin puzzle. Maybe it's not puzzling to you, but it was certainly in the 80s. We know the spin of the proton is 1/2. According to quark models, that they were very successful at that time understanding QCD, or they thought it was very successful understanding the hadron structure. They were expecting that the 3 valence quarks in the proton should carry 1/3 of the proton spin, and they did experiments and they found surprising results. Not only they were very, very noisy and kind of inconclusive, they were not capturing the 1/2 of the proton, and that was the proton crisis. So I did ask around people who were active at the time, and I said, well, was it really assumed crisis now that we know QCD and so on? The statement, I think Abhay was telling me this, that high energy physicists were not talking to nuclear people, and QCD didn't understand much of it. So there was a bit of a chaos and not good communication between scientists. But there was also a scientist, Elliot, who was interviewed, I think, by New York Times, and it was him who introduced the word crisis, and that was in the New York Times. And Mauro, okay, that's good.
Yeah, they wrote this paper called "A Crisis in the Proton Model."
Okay.
Where is the spin?
Yes, and that was also grab the attention of media, not social media, the regular newsletters.
Titles are important.
Yes, it's important to ask for funding. You will all go, hopefully, in academia. You will have to make a case for your work. You need to be able to advertise the things that you're doing. So choosing the right words where you are at the same accurate and not misleading, but emphasizing the importance of what you're doing, obviously work, because we are now talking about EIC and the proton spins after so many years. Okay, so there are still open questions. For instance, what is the different components? What are the gluon contribution? What is the orbital angular momentum? And so on. And luckily, lattice QCD can do that from the theory side. When you do experiments, you have to respect what nature is going to do at the time of the experiment. You can try to do your best, and I'm not an experimentalist, so I don't know all the details, but you can try and control as much as you can. But you cannot isolate QCD, right? Nature is going to do what it wants to do, and sometimes new physics might come out of this because experimental data may not match the theoretical data. The good component of theory, and in particular lattice QCD, which is capturing all the non-perturbative aspects of QCD, is that we can isolate every contribution of QCD, and we can calculate what is the total spin, what is the intrinsic spin, what is the gluon speed, the quark orbital angular momentum, and so on. And all of these have their own operator. Necessary computations, they are also related to the physical quantities. For instance, the axial charge is related to the intrinsic spin. So you have in the operator you want to insert, you have an axial operator, not a vector operator. Quark momentum fraction and gluon momentum fractions are also related to the orbital, to the total spin, and indirectly to the quark orbital angular momentum. Some plots here just to see that we actually did these calculations. These are from many, many years of effort. It's kind of a history diagram as well, because remember how I said last time that in the past we used to simulate quark, assuming the quark masses are very heavy, reproducing pion masses or all the physical masses to be very heavy. That's what this x-axis mean, is the square, is the pion mass squared in GeV squared. And 15 years ago, that was pioneering, and 12 years ago, this was pioneering, and 10 years ago, we were here. Now we are at this point where is the physical parameters. So we are reproducing the correct mass spectrum and energy spectrum of particles, meaning that we are now simulating the parameters encountered in nature. This is the axial charge, is very, very well known experimentally, is this star over here. And there is an update of this plot that shows that the lattice data are in agreement with the star and much more accurate than what I have here. Other quantities is what is the quark momentum fraction carried by what is the momentum fraction carried by the quarks and the gluons. Again, here, modern calculations sit at the physical point, and this is a more difficult quantity to extract experimentally. It takes input from theory and different models. So you have black points that do not necessarily agree to each other because they're depending on models. Yes.
And these are the fully integrated distributions?
What do you mean? This is from Mellin moments.
Okay.
The spin is related directly to local operators. So you don't have to go through X dependence. You could, and then if you have the X dependent, you integrate out and get the spin, but you don't have to do it. You can go directly and it's easier this way.
So then this would be comparable to like an X integrated distribution?
Yes, yes. It's a Mellin moment of the helicity PDF. That's a very good point. So I chose a couple of examples. One is going through Mellin moments. Spin is going through Mellin moments. So I'm having all of these operators now. The other example I'm going to talk about is from X dependence. Okay, so I talked about all of this, but I want you to take a moment and appreciate the numbers you see here. This is the axial charge. And it's very well known experimentally. As I said, these are lattice data for the up, down, strange, and sharp quark. And of course, for a proton, the up and down have the dominant contribution. These appear in the valence sector. But in the C, the strange and charm quarks are present. They're not as heavy as the top and the bottom. We don't talk about top and bottom physics when you study the proton. The proton mass is low enough not to encounter any phenomena related to heavier quarks. But look how the strange quark is an order of magnitude less than the down quark and the up quark, of course. And the charm quark is a contribution from the charm quark is another order of magnitude less than the strange. Look how small these numbers are, and look at these errors. These errors incorporate not only statistical, but systematic uncertainties, meaning continuum extrapolation and being at the physical point and volume effects and discretization effects and so on. So see how how difficult it is to get such a small number from very noisy data. However, this seems to work. For some quantities, we have reached the precision level. The spin is one of them. Okay, momentum fraction carried by the quark. This is related to the total spin. I don't want to focus too much about this. What I want to emphasize is that lattice QCD successfully calculated all the contribution, meaning by looking at the appropriate operator, we can see what is the momentum, what is the percentage of the momentum carried by the up quarks compared to the proton, of course, the down quark, the strange quark, the charm quark. It's interesting to see the sum of all of the quark, which appears to be about 60%. The gluon was also done with a diagram that probes gluonic contributions. That's about 40%. And if you add all of the quarks and the gluons, all of them together, you get about 104% with an error that is 10%. But you see how you have identified from lattice QCD. I'm sorry, what was I talking about? Spin? If I was talking about spin, I meant gluon, momentum fraction. Yes.
So in this plot, I was interested, why don't you use the total, which should be one, of course, to fix the systematics for the other?
Okay. That would be cheating.
Yes.
So you answer yourself. Okay, for a long time, when we were not able to calculate gluon contributions, when we were not able to see the C sector and capture the strange and the charm, we were doing what you said, saying that approximately the up and down that are easier to extract are about 55%, 53% or whatever. And you say, if I accept that the momentum fraction has to be 100% identified, I remove this 55%, the others have to be 45%, that's great. But if I was an experimentalist or a theorist, I would say, why do you have confidence on your 55%? What gives you confidence? So yes, it was use this argument to say we expect the gluon to be about that time, but the right thing to do ab initio is to not, when we did this calculation for the up, down, strange, charm, and the gluon, we had no idea what the other was. And we did every one of them separately. And then it was like, this stressful month where you say, okay, well, I'm going to get out of all of this. And you see the momentum fraction is 100%. So this is a big success of the field, being able to say, I control my systematics. Why is this important? Because now when I show you GPDs, you will have a more positive attitude that we did our due diligence, right? That we understand our systematics. It took, to get this kind of plots, it took 30 years to be able to reach the point where we do simulations at the physical point, big volumes, small lattice spacings, and so on. So now we have a bit of confidence to do more complicated things where we don't have experiments or we don't have any guidance. Does this answer your question?
Yes. So if I add one more question, so that says that the individual estimations are not correlated among each other, apart from coming from the same ensembles, I guess.
Yes, they're not, they don't, well, okay. Up and, how can I say this, not to be confused? When you calculate these diagrams here, these are up and down quarks. This incorporates up, down, strange, and charm. And this incorporates, it's only the gluons. So when you do this one, it has absolutely zero information of the other two. It doesn't take any input from any component. So in that sense, yes, you can call them independent, and you have to calculate on the same ensemble, otherwise it will not work.
Thanks.
Okay, so we have seen the momentum fraction that we reach 100%. In a similar way, I can see the total spin, which I find to be 100%. Spin 1/2. We have found that, and we have seen the intrinsic quark spin for the up, down, strange, charm. It's a tiny, tiny number, but we found it. And also by comparing the intrinsic spin and the total spin, we get information on the orbital angular momentum. Maybe Yoshitaka mentioned this, that orbital angular momentum, there is not a good operator if you do a gauge invariant decomposition to give you that component. However, if you know the total spin and the intrinsic spin of quarks, you can find the quark orbital angular momentum. And I'm talking about the quark spin here. Okay, so let me move on to the other quantity I wanted to talk about. Now we are doing novel methods, no more Melling moments. The first thing, of course, is to study one-dimensional quantities, and polarized PDF has been studied since 2014. Personally, in my research, we have moved to GPDs. We no longer care about PDFs. Even though I don't say this to LHC people because they expect to give them, they ask for PDFs at accuracy, I don't know, less than 1 per mil. My answer to that is that Lattice will never give you this accuracy. I don't care personally. I don't think I will convince funding agencies to give me support to do that. But I think working with global analysis, that's where we can combine things and try to incorporate Lattice into experimental data set analysis, and that might be able to refine even better. That's very promising for transversity, for instance, in the tensor charge. But we are never going to reach the 1 per mil systematic uncertainties because these methods have systematics to incorporate. But this is a lot of collaborations doing that. GPDs is where the field is moving, and especially because EIC influence. We want to get GPDs and TMDs. I am peripherally involved in some TMD calculations, but I'm not going to talk about this here. I don't even have time for that. But GPDs are a good candidate because it's an extension of PDFs in terms of how do you calculate these matrix elements. You have matrix elements. In a PDF, you do not have momentum transfer between the external states. In a GPD, you do. And experimentally, you can access them through DVCS, DVMP. Yoshitaka talked about this. Maybe he has talked about new observables, but there are a lot of challenges. I'm not going to go into this, but there are a bunch of things we don't know how to do, how to get the X dependence, because we do not get the GPDs directly from the DVCS and DVMP at least. Phenomenology of so many parameters is a headache, it's a nightmare rather. They have multidimensionality. Also, we have a lot of GPDs, and disentangling them becomes problematic. However, and that is to say, let's complement from theory and lattice QCD. And considering we can do the proton spin so well, we can do electromagnetic form factors, we can do axial form factors, we have a bit of confidence of having tested the field. However, these particular calculations, they're not fully tested. We are developing things. There are a number of systematic uncertainties that we have to understand. So we are not ready to give numbers to people. We are ready to give you qualitative results. using this pseudo and quasi distributions approach, this particular is quasi distribution, we were able to extract GPDs. This is some data just for you to see what lattice data looks like. Is basically, if you look at either of them, this is the unpolarized H and E GPDs. These come from the vector. If you take Mellin moments of those, you get the electromagnetic form factors for the proton. You get the charge radii. But since you have better tools to study them directly, you don't want to go through quasi and pseudo distributions to do that. It's too complicated. Go directly from local operators and Mellin moments. But what you see here is something you cannot see from the Mellin moments, and is basically the X dependence. That we get from the lattice data because we don't need to do an OPE. And you see here different values of the momentum transfer. So in reality, these are 3D plots. This is for the axial, the helicity, H tilde GPD. So it's just to demonstrate the field has significantly progressed. However, there are a lot of issues that you have to be aware of. When you see this kind of plots, do not believe anything that comes out of around x equals 0. Small x physics is not something we can do with these methods. And when I say small x physics, 10 to the minus 3, 10 to the minus 5, some people say, and also the large x region. And that has to do with the formulation of these methodologies. They have uncertainties. There are regimes where this matching between lattice data and light cone, it breaks down. And you have higher twist contaminations and a number of systematic uncertainties. So when you look at these plots, I would say let's focus around 0.2 to 0.8. That's what you should look at. That's where lattice can do a good job. And we can cover a wide range of kinematics, so this can complement the data. We have actually given this data to people who want to play around with their models. Ishmael Zahid, who is here, and his postdoc, Florian, have taken this data to see how it compares with the models. Some global analysis, people want to incorporate them in some formulations they're writing. So there is a lot of demand for this, but we should always keep in mind that these are not accurate data. They're not precision data. It's kind of a guidance. It's better than not having anything for a given kinematic and implementing a model assumption. It's better to have some lattice data that come out from QCT, even though we understand there are uncertainties. So my student, Joy Dorciello, is in the room and is working on GPDs for the pi and the k. And if you want more practical details, you can talk to him. I'm sure he's happy to help. Okay, so I have talked about different approaches. So some of you have asked on Monday night, which one is better? And I say none. All of them have advantages and disadvantages. And this is now what I have shown you previously have been extracted with quasi-GPDs. This has been extracted with the same data using pseudo-GPDs. The other approach where you go through Joffe time and then you take a Fourier transform. And of course, the most interesting component is to compare them and see that how well they agree. We're doing a good job in general. In general, the shapes are similar. The errors you see here do not contain systematic uncertainties yet. So you should just make them wider, add 20%, I don't know. We have not estimated that. It's only statistical for the time being. The negative X region is the anti-quark region. That's very difficult to extract, and you should also not take that seriously. So I would say quark region, which is the positive X, 0.2 to 0.8. These are the regions that we can do well and maybe excellently in the future. Okay, so I already mentioned complementarity, a couple of thoughts before I finish. Lattice is not in one corner, theory in another corner, and experiment in a third corner. We should all work together. That's why these schools are great. You will be the future scientists, and you better start talking to each other and not wait 20 years to realize I don't know the language and the terminology of experimentalist, and I'm a theory, and I am forced to talk to them because I don't understand them. So talk to each other, learn what are the terminologies, what are the symbols you're using, and what are the constraints. I think that would be extremely valuable to consider and talk to. And the synergies have begun. I did mention already some of this data have been given to theories and global analysis. I do have a summary for that. Alexei has been working on this transversity, and his group has used some of the lattice data and narrowed down this for the tensor chart. They narrowed down the errors if you incorporate the lattice and so on. So there are a number of calculations that JAM has done, for instance, and so on. So there is some progress. However, this is not where it has to be. We do not talk closely enough with other people. Some efforts show that comparing with models and incorporating lattice data can narrow down your band. So we are on the right track, but we are not there yet. All of these are exploratory. And one of the big success of the field of nuclear theory is that the field has come together and formed topical collaboration. SURGE collaboration, who is funding or co-funding this school, is one of the topical collaborators. I am a member and a PI of the quark gluon tomography collaboration. We call it QGT. And basically is a group of lattice practitioners, phenomenologists, and theorists. Alexei is a member of our collaboration, belonging to the phenomenology, right, Alexei? And the idea is to talk to each other and come up with the right formulations and the right platforms to eventually incorporate JLab and EIC data on GPDs with input from lattice QCD and theory into a single platform and give it to the community. So it can be a database and a platform where we can better understand GPDs. So that is our topical collaboration effort. And there are other different efforts I'm not going to go into. But with that, I want to just summarize and say that lattice QCD is working very intensively in hadron structure investigations. We are very confident that when EIC is operational, we will be able to also provide input from first principle. We have a lot of work to do, but there are a lot of promising results. And I think the last point is the most important one, which is we should put a serious effort into synergies and collaborative efforts if we want to see this field succeed. And with that, I want to wish you good luck with your studies and your careers. I see many of you in meetings, and I will see many of you, and just keep fighting for good science. That's my message. Thank you.
Thank you. Yeah.
Join
Join
us
us
here.
there. Questions?
Yes.
Pretty close to the beginning is slide 5. You were talking about, I guess, some pros and cons. I think it was about calculating PDFs and stuff. One thing you said is that your signal to noise ratio gets
Yes.
worse with
Mhm.
covariant derivatives. I
Yes.
wasn't really sure how or why.
Okay, so let me show you. Here. So you have these covariant derivatives. Q and Q bar correspond to the quark fields. And if you look at the arguments of this operator, is Q and Q bar are local. They're at the same point. So you have Q at some X derivative and Q bar at some X derivative or multiple derivatives, and then Q at some X, and X is the same. When you apply the derivative, you make this object to be extended, right? You shift derivative of the field at X, it becomes the field at some point X plus minus 1, depending on the derivative where it acts. Because here you have derivative which is left and right, so it acts both sides. So the high Mellin moments, it means more derivatives. And you take this object which is local and you replace it with somebody. When you say what the derivative does, you replace your operator with an extended operator where the fields move further away from each other. And when they move away from each other, they're far enough where the gauge noise enhances and so on. That's what I mean, that the signal decays. I don't have a plot with me here, but this is the n equals 0 case. If I do n equals 1 and 2, which this is where we have managed to reach, is even introducing one covariant derivative, the errors increase significantly, and also the number of collaborations decrease significantly because people don't want to invest a lot of computer time to study something that's very noisy. They want to do something different. So that's what I mean, signal to noise increases.
Brilliant.
Do you think there will be in the future any attempt to modify lattice methods for small x physics?
Well, I want to say no, but considering that if you asked me 15 years ago, do you think we will ever get X-dependent distributors, I would say also no. I would say that as of now, the methodologies we have, they're prohibiting us to get small x physics because I can't get it. I just don't trust it. The systematic effects are very large. But if there is some effort also from theory, not from lattice, when we're doing this kind of X-dependent distributions, we have received great support from theory because the theories are making the connections between lattice data and light cone. So if they find formalisms that can take into consideration high twist effects and eliminate them, so the more you improve on all of this, you have higher order calculations. Then this 0.2 to 0.8 starts expanding. So now, but now if you're asking me 10 to the minus 5, I would say likely not, but you can push the boundaries by better improving the methodologies.
Great.
When you were like defining your PDFs, like a matrix element, how do you, what is the external state in the lattice?
It's a product.
I mean, you have to have an hadron and then you apply the
Operator?
The operator.
Yes.
How do you define them, or how do you represent the hadron?
It's done through, okay, we do not actively simulate anything that looks like a hadron. You basically write down an interpolating field that has the quantum numbers of the proton. So it's an operator that has 2 up quarks, 1 down quark, the right spin or structure, and then on a piece of paper, you do weak contractions. So you have proton interpolating field, a proton interpolating field in the bra and the ket, and in the middle you have quark, the operator. And if your operator is a quark operator, you decide what quark are you probing? Are you probing up, down, strange, or charm? And you write that there. And then on a piece of paper, you start doing all the possible contractions. If you have an up quark operator, then your up quark can contract here. The up quark, if this is now an operator that has an up quark, the up quark can either self-contract or it can contract with the up quarks of the external states. So it's a weak contractions where you create propagators, and that's what you actually simulate. You simulate all these propagators. So in that sense, I do preparatory work on a piece of paper where I take an object that looks like a hadron or like a proton, but I don't know what kind of state that proton is. If it's going to be ground state, excited states. That is why we do the analysis I mentioned last time, where we do a plateau fit. So we make sure that we allow the states to decay to its ground state.
So you just take into account all the things that are compatible with the
Yes.
quantum numbers that you know they are.
Yeah, and the way you say it, it sounds like we're doing a good job, but I would put it differently. I would say we have no option, but we cannot isolate the ground states. There are techniques to make the excited states suppress very, very fast, doing other kind of interpolating fields and so on. But in principle, I have no option but to accept that anything that has the quantum numbers of a proton is going to show up in here. And my only tool is to stay away from the moment it was created and was annihilated, because that's where you have high contamination from other states.
Go to slide
18.
So you mentioned like how for the momentum, you didn't enforce the sum rule
Yes.
in order to don't cheat. So I was wondering here, you do use, for instance, the some combination to extract.
Yes. So if you look at the operators, there is, okay. If you look at the decomposition here, this one, this is G's decomposition. There is Jaffe-Manohar decomposition also. It gives you access to slightly different quantities. The problem with that is that it's not gauge invariant. And calculating non-gauge invariant things on the lattice is very problematic in terms of knowing what you're calculating, connecting it to physics. So what has not been, so you see here there is a Q, right? Q is the flavor of so you're doing up, down, strange, and charm quark. Each one of those components, so I can calculate on the lattice the total charge. So this JQ, there is an operator that relates to that. There is an operator that relates to the intrinsic spin, and there is an operator that is relating to the gluon component. There is no operator that relates to LQ. So you calculate JQ and you calculate intrinsic contribution for that flavor, and then you subtract them to get L. However, that doesn't affect these kind of pictures here, because all of these correspond to an operator that can be calculated in the lattice. Same for this total spin. This is calculated from the lattice. Same from the intrinsic spin. All of these are calculated from the lattice. The orbital angular momentum, and these you see we satisfy the sum rules, both here and the momentum fraction. But if I look at this, you can either pretend this, I'm not going to show it because I don't get it directly, or you can say, I can take a glimpse and subtract the intrinsic spin from the quark spin and find what is the orbital momentum for that quark. So that doesn't change the fact that you don't have any input to check this 100% here, nor for the momentum. So these are totally independent, because put the orbital angular momentum here, which is what you see here, still all of these components do not talk to each other. It's just that this object is the difference between two measurable quantities.
And is it that operator doesn't exist, or is it difficult?
It doesn't exist. If you want to understand a bit orbital angular momentum, you have to go non-engaging invariant way. There are some efforts. I think that Michael Engelhardt, who is at New Mexico State, he's doing some of this with Japan Manohar decomposition. Yeah.
Outstanding questions. You have maybe 4 minutes after we thank you again.
So let's take a half-hour break before the tutorial, but if you need to download or pull the Docker image or have any questions, warm up, I can look at those, but we'll start with 2:45.
So I think so, yeah.
Right.